What is the meaning of Einstein's statement, God does not play dice? Does that mean Einstein did not believe in probabilities? Does that signify Einstein's diffidence in quantum mechanics? Is it that he believed in something else? Or is it that Einstein's soul was in contradiction with something else? How can that happen who has given birth to the concept of quantization? Well, in this video, I'm going to explain this famous statement in details and will take you through a deep philosophical journey into Einstein's conflict as well as agreement on the laws of physics and explore some of the bizarre phenomena of science, thereby comprehending the actual meaning of this statement. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to this very new and different type of video on explaining the philosophical and scientific meaning of this statement, God does not play dice. Well, first, we don't have a title or any table of contents to cover today. First, we would like to understand the statement as it is given. So first, we would take this statement and understand what is the meaning. Well, if I take the statement, God does not play dice, then the first one I would circle is God. Now, there has been a lot of misinterpretation among various students and various groups that what actually Einstein meant by the term God. Now, I would say that he actually meant how nature operates, a orderly harmony of events, which we will see has been quoted from some of his statements later. And we can say that it is a deterministic system, a system which obeys the laws as per classical physics. And it is a system which reveals itself in due process of time. Now, if I take these three words, does not play, it would mean that Einstein refutes something or he is not comfortable. Rather, we would say that he is uncomfortable with something which would need to explore. And he used the word dice, that means a probability of events. It also means it is a non-deterministic system and living by chance. Because when we throw a dice, we don't know what the dice would eventually reveal into. So these are the three lines very important before we start the video to understand the literal meaning of God does not play and dice. Now, this actually, gives the basic understanding, and it also takes into something called inherent randomness. And this is something we are going to explore because this has got a deep philosophical and scientific meaning. But before we dive deep into understanding the statement, we need to understand when we talk of inherent randomness, probability of events, what do we mean? That is coming up in this part of the video. We would talk about what is called the birth of quantum mechanics. In general, when we talk the birth of quantum mechanics, we talk of either Planck's discovery of black body radiation or something else. But I would like to give you a different approach today. And I would like to take you back to the first Solvay conference which took place in 1911. And the famous physicist Hendrik Antoon Lorentz was the chairman on the first Solvay Congress, which was held in Brussels around 30th October to 3rd November 1911. And the subject was radiation and quanta, and that marks the birth of quantum mechanics. This conference looked at the problems of having two approaches, namely classical physics and quantum theory. Albert Einstein, as you can see in the photograph, was the second youngest physicist present. Other members of the Solvay conference were Marie Curie, Ernest Rutherford, Henri Poincaré, and various other physicists. Now, why it is important, because in the first Solvay conference was participated by 25 participants through invitation. Einstein made his debut to the non-German speaking people, and this was the first time that classical physics and quantum physics were brought on the table and duality of wave and discrete packet of energies were being discussed. Now, this is definitely considered to be the turning point in modern physics where quantum theory actually come up front. There was a letter of Marie Curie recommending Einstein's position as a teacher, and this was Ernst Solvay's decision for sponsorship. Now, this is something really interesting. If you want to know more about how the history of Solvay conferences started from first till 2019 or so, you can look into my playlist. There is a separate video dedicated with details into something called the Solvay conferences, which gives you further details. Now, why I brought this topic into this part of the video, because this is the first time which was the inception of quantum physics. So you see, the classical physics and quantum physics, the wave-particle duality was first there, and quantum theory was first revealed to the world through the discussion of these 24 eminent physicists. Now, what is important is that Einstein has already made an important contribution in the physics, in the area of quantum physics. What is that? We will quickly discover in the next part of our video. Now, we all know that he has been awarded with photoelectric effect and what is called quantization. Before we go into understanding the statement, God does not play dice, I would like to give you a quick review of what is a photoelectric effect. Now, as you see, photoelectric effect is the emission of electrons when electromagnetic radiation such as light hits a material, and the electrons emitted in this manner are basically called photoelectrons. Now, the experimental results disagreed with classical electrodynamics. This is basically the equation more or less of photoelectric effect. Now, the experimental results disagreed with classical electrodynamics, which predicts that continuous light waves transfer energy to electrons, which would then be emitted when they accumulate enough energy. But an alteration in the intensity of light would theoretically change kinetic energy of the emitted electrons with sufficiently dim light, resulting in a delayed emission. And what we find out is that the experiment results instead showed that electrons are dislodged only when the light exceeds a certain frequency, regardless of the light's intensity or duration of exposure. Right, so it shows that the experiments in place of being continuous waves discuss something which is called energy packets, and these are called photons. In 1905, Albert Einstein published this paper advancing the theory that light energy is carried in discrete quantized packets to explain experimental data from the photoelectric effects. So here it is, light energy is carried in discrete energy packets. So what we found is that above a threshold frequency, photon has the required energy to eject a single electron, creating the observed effect. And this was the first key step in the development of quantum mechanics. Now you see that this is such an irony that the person who himself developed the first step, that light is not a continuous thing, but it is a discrete quantized packets, and these energy packets are known as photons, and made the first key step towards development of quantum mechanics, made such a statement which shows that he doesn't agree. We will further go ahead and proceed and look into these phenomena. But before that, it is a right time to look into what was the actual letter, the original letter, which cited this single line, God does not play dice. Let us look into this part of our video coming up next. So the time we are talking about is around December 4, 1926. Remember that 1911 we already had the first Solvay conference. People had agreed further that quantum mechanics is going to take an important place in the arena of physics. Now, Einstein's letter to Max Born. I would like to read it quickly. So this is Born-Einstein letters, and you can read it quickly, that quantum mechanics is certainly imposing, but an inner voice tells that it is not yet the real thing. The theory says a lot, but does not really bring us any closer to the secret of the old one. I, at any rate, am convinced that he is not playing at dice. Waves in three-dimensional space whose velocity is regulated by potential energy, for example, rubber bands. Right? I am working very hard at deducing the equations of motion at material points regarded as singularities given the differential equation of general relativity. Your best wishes, Albert Einstein. Now, I would like to make some quick observations of this letter. First of all, you see that he says that quantum mechanics is certainly imposing. That means it is grand, it is impressive. So it shows Einstein has assumed or has admitted that yes, quantum mechanics is indeed the answer to some of the unanswered questions of nature. But an inner voice, this inner voice actually is speaking of the Einstein's deterministic nature, because remember, he is a classical physicist who would always believe in certain determinism of nature. So that is why he talks of an inner voice tells me it is not the real thing. Now there is another statement. He says that not really brings us closer to the secret of the old one. The old one actually means what he's talking, and he struggled till the end of his life, the theory of unification, or we can call a theory of everything. Another important point, he is not playing dice. At dice is a German translation for English, so this signifies. But what is ignored in this letter that most of us do is this line, regarded as singularities. Now, we will see further that we will try to decipher and we'll try to make out more what he meant by regarded as singularities and what actually speaks up. Let us look up in this part of the video. These are points in the model where values tends towards an infinity, or we can say something undecisive, right? So we see that this is the original letter. The upper portion has been omitted, so you can read it or take a kind of a snapshot of the screen. You will have a little patience. My son-in-law is certain to read the play so and so. So I will just take a pause and you can just note down or take a screenshot of this letter. This was the original letter on 4th of December 1926, written to Max Born and by Albert Einstein. Okay, now few of the things which comes up from this one is this. I am working very hard at deducing the equations of motion of material points regarded as singularities. Now, I won't be explaining further because this is a different part of equations of motions which relates to some three-dimensional thing can be written easily using motion material points method. But what I'm trying to tell is that equation of motion at material points, right, is something which relates to differential equations, and these are something which relates to certain condition to singularities when the entire equation blows up to infinity. So what I'm trying to make a point is that not only the statement that God does not play dice, but this statement also shows that Albert Einstein was not okay with singularities, not okay with undefined values, and his quest is trying to find out something certain within the uncertain world. So this line has been ignored. I think nobody really mentioned, I made my research, that what is material points, and is struggling to define those singularities into something which is certain. So we find Albert Einstein's internal quest and his coincidence trying to find something certain within the uncertainty or the singularities or the undefined values which results from the system. So till now what we have understood more or less is basically the meaning and the foundation of quantum mechanics and his letter, what he meant and what he is not happy of. Now, what are the factors that actually made Einstein not happy, or I would say Einstein was not comfortable in his own mind and thought? Let us see into the next part of our video. So first we would see into what is called a wave function and probability in a very non-mathematical but a much more philosophical manner. So you see that wave function is defined by this Greek letter psi, and a wave function is basically nothing but a probability distribution which provides a probability for the outcomes that where a particular particle or a subatomic particle would be. Now, if I square this value, this can be, defining either a spin of a particle or it can be different energy levels. But the thing is that because it defines the probability, what we do is that we square this value, and from there what we get is called a probability density. Probability density in general means that how much probable is that we can find electrons or subatomic particles at a certain location. So here is a nice graph which shows the psi and the position, and these are the areas where most possibly we are about, or we can find out there's a high probability in order to find the electrons at a specific place. So these curves, the bell-shaped curve and the blue lines, shows the probability density. Now, the probability density of the wave function actually shows the first cornerstone that quantum mechanics is not deterministic, it is something probable. But there are certain other things also which comes up. Now, you see that the probabilistic nature is being defined as it is impossible to predict the certain outcome of a single experiment. That means that if I shine a kind of a light from here to this red point, then if I want to find out exactly where this ball or the electron would go, then there might be a 42% chance over here and 58% chance that it would land here. So only thing that we can predict is the probability. So now if we visit the same statement, you see the theory says a lot but does not really bring us any closer to the secret. That means any specific deterministic thought cannot be found out. This is the first thing which actually speaks that the theory speaks a lot, but it does not really bring close because it all deals with probability. Question is it that only the probability was disturbing Einstein to make such a statement? Let us find it out in this part of our video. This is something important which we called quantum superposition. I would like to define quickly quantum superposition in very simple mathematical term, and then we will go to understand in a layman's language. Now, if we assume that a state of a dynamical quantum system at a particular moment is psi, this vector, corresponds to a vector, and if this state is the result of a superposition of other states, this var phi and this chi, then it can be represented as a linear equation like this, right? Just an addition. So what is the superposition principle? The superposition principle actually says that every vector or a ray we can call in the Hilbert space, don't worry about Hilbert space, let us consider space just for example right now, corresponds to a possible state given two states, this one var phi and this symbol chi, and what we can get is that another state as a superposition of other two states, which is just the addition of this. This is a kind of a strict mathematical definition using the Bra and Ket Dirac's notation. What I would like to quickly mention is that remember that superposition is not just it is in quantum mechanics. It is also present in classical mechanics, which is the classical superposition. It is just adding a position vector to another vector where we get a third position. For example, we can say that the net response caused by two or more stimuli is the sum of the response caused by other. So we can say that, for example, if input A produces response X and input B produces response Y, then input A plus B would produce a response of X plus Y. It's a very simple kind of a definition. It is not a classical superposition, it is a quantum superposition. Why? We will just see the difference more closely between quantum and classical superposition. But before that, you see this one is basically a classical superposition, right? This is a classical superposition. I would say here what happens, it is a superposition, remember, of two orthogonal states, orthogonal velocity, sorry. It is unlike any either basis or alone. And this is the quantum superposition. It is of two orthogonal states. The state is unlike either basis vector alone. So this generally this psi is sometimes called simultaneous in both states, but it is just the superposition. So this is, the classical superposition of two vectors. Adding quantum superposition is something where we add the two states. So here is the velocity vector, orthogonal, and this is the superposition of two orthogonal states. Let us try to understand quickly in layman's language. So an electron is simultaneously in all the locations covered. So here you see in a classical system it is either outside or inside, but in a quantum system it is both inside and outside. So when we toss a coin, this is both in head and tail conditions, but when it falls down, it is either head or a tail. And this has been brilliantly explained by Schrödinger in his famous Schrödinger's cat analogy, where he tells that the cat is both alive and dead at the same time. This is also something which Einstein was not comfortable with, what is called quantum superposition. How can a state is present in both the places, or how can a cat be both alive and dead at the same time? But is it only this quantum superposition that made the great scientist feel disturbed? Let us see in the next part of our video. So we will talk about something precisely important, and that is something which really disturbed Einstein than anything else. It is called quantum entanglement. Now, what do we mean by quantum entanglement? So any object or any event can influence another object or event only if you have allowed light to reach there. And this is what we call locality, and this is one of the foundation cornerstone of classical physics. That means if I got some object like A and some object like B, then we cannot influence that object B until there is a light or any kind of a communication which has gone. And obviously, because the speed of light is the highest, and special theory of relativity tells that nothing can travel more than the speed of light, so any communication should be slower than that. But if we get the same things A and B, and now if we shine a light which goes over there and reaches, then we can tell that yes, it influences. So locality, as you understand, is something that there should be an event or a light or anything, a sort of communication which reaches. Until that, we cannot say that one object influences another. So no cause can cross the distance of light, because here I have given an example. The fairy cannot wave her magic wand instantaneously and the pumpkin turns into a coach from Cinderella. Now that is something really which wondered Einstein, because we have seen in quantum entanglement, or rather we would see in quantum entanglement, this is basically an exception. So Einstein thought that what if the locality is not present? Is quantum mechanics non-local, or is it something which violates the basic laws of physics? Let us find out in the next part of our video. So we talk of quantum entanglement, which happens in quantum physics, that each particle of the group cannot be described independently of the state of the others. That means however long they are separated, they are entangled or joined with each other. So I would say, if a pair of entangled particles are generated in such a way that one will instantaneously affected with other. So these two particles are actually perfectly correlated to each other, and even if they're billions of lights apart. So if they're billions light years apart, then we have to send a signal which is more than the speed of light. And this is what led to the famous paradox of Einstein, Podolsky and Nathan Rosen, which we called EPR paradox. The question is that, is it something happening where the speed of light, where we are transferring something more than the speed of light? Because the moment one thing happens, the other thing changes. Let us see more illustrative examples. Things will become clear. So here it is, if a pair of entangled particles is generated such that their total spin is 0 and one particle is found to have a clockwise spin on first axis, that is, say for example a spin up, then the spin of the other particle measured on the same axis is found to be anti-clockwise. That is, it has got basically a kind of a spin down. Now see, what happens particularly is that even these two particles are quite distant apart, billions of light years, yet a small change in this particle causes a small change here, and that happens instantaneously, although they are distance apart, right? Now here I would like to make a point that this is not actually the case. I will make a separate video because there's a kind of a, I would say, misconception that quantum entanglement means things are traveling at speed of light. No. I'll give you a classic example. If you toss a coin up and it falls head, right? It falls head, then obviously the bottom part is tail, right? Now if I ask you when that tail occurred, what would you answer? If the head is right on the top of the coin, that is, it has got head which we can see, then the bottom part is tail, right? If I ask you when that tale occurred, what would you answer? Let me know in the comment box. Okay, let us go further and we will see that this distance apart, yet the changes happened immediately and instantaneously, and that is what bothered Einstein. So in this paper, which is the EPR paradox, published on May 4th, 1935, issued of the New York Times, the thought experiment involves actually a pair of lasers, particles prepared that would later become entangled. And this was the title: Can quantum mechanical description of the physical reality be considered complete? So Einstein, Podolsky and Rosen pointed out that in this state, if the position of the first particle were measured, the result of measuring the position of the second particle could be predicted. If instead the momentum of the first particle were measured, then the result of the momentum of the second particle could be predicted. They argued that no action taken on the first particle could instantaneously affect the other, since this would involve information being transmitted far faster than the speed of light, which is forbidden as per special theory of relativity. So here is the paradox. Einstein attacks the quantum theory. These three gentlemen produces a thought experiment where they tell that one particle can influence the other. Information being transmitted from one to other. So question rises, is quantum theory then non-local? Because locality, as we have seen, represents something which should be transferred from one part to another, and then only the event can happen, then only we can see something on the other part. But here it is telling that it is instantaneously being transferred without a fraction of a second's delay, even they are billions of light years apart. So we will now see what is called a wave function collapse, because this is again something which really perturb or disturb Einstein. Now, when we talk of wave function collapse, I will take a very simple example. So if I take a ball and I'm throwing in this direction 20 meters per second, and if I throw the ball in this right direction, then I know as per classical mechanics that it would say, suppose, transfer or travel 130 meter in when it reaches t equals to 20 seconds. Now, if I repeat the same experiment using the ball and throwing it on the right hand side at the same speed, we know that it would travel 130 meters and reach at 20 seconds. And even if I do the third time, every time it would be the same. But here you see that this is actually not what happens in quantum mechanics. In quantum mechanics, this is what is called superposition. So one electron or one particle is at both of the states. So what happens? It exists in a quantum superposition until and unless we observe there is an external interference. So the moment we observe, that means we are doing some experiment to move these particles either way or the other, we see there's a 30% chance over there, 20% chance over there, or maybe a 10% chance over there. So the wave function collapses almost randomly, giving us no chance to find out where the ball or the electron would land upon. Whereas on the left hand side, you see classically we can find out exactly where the ball would land upon. So especially if you do a kind of a huge number, I mean to say we do it 100 or 1,000 times, then we get a probability distribution. But for individual understanding of a particle, it is impossible. So the function or the wave function collapses almost randomly. So here is Einstein, and he is thinking that how can this happen? Because the quantum physics tells, or the classical mechanics tells, that locality exists. But here we find that it exists in both the state, and certain things, the prediction is almost random and we cannot find it. So what he thought is actually something like this. He thought that there might be certain hidden variables which are local and deterministic, and we are unable to find that. Unfortunately, John Bell, another physicist, has found out that under all experiments which are being done, Einstein was partly wrong, and he ruled out the possibility that they cannot be local and deterministic. Well, that is a different part of the video, but we will now turn up to something which Einstein was really worried about. How can a change here instantaneously cause a change over here? And that too happens instantaneously. This was the thought that how this can happen. Is it that the laws of physics are breaking down? Is it that something hidden is there but the laws of physics are unable to explain? And this is when he made this famous statement, a spooky action at a distance, which our Nobel laureates Antony Zeilinger, Alan Aspect has proved there is no spooky action at a distance. Okay, so these were basically the factors which made Einstein very worried, and he came to this statement, God does not play dice. So you see, if we move from Descartes and Isaac Newton and Galileo, and we take the classical physicist, and we find there is something really deterministic and future is predictable. So our brains are really wired to see something very definite. We see a fish as a fish, a cat as a cat, and a chair and a cup of coffee or mug as something the same. So the problem was not actually even with Einstein, but our mental human brain and thought is something comfortable with deterministic and certain behavior. Now, also we see that these classical physicists, when we move from here to the quantum physicists, starting with Feynman, Planck, Schrödinger, Dirac, and all those people. So what we see is that nothing is definite. There is always a probability. There is always a chance that we are living into, and there is a range in distribution that will be helpful for us to find out something. So taken all this together, our good old dear professor was very worried. So you see the random collapse of wave function, the quantum superposition, the quantum entanglement, and the wave function probability troubled really Einstein's mind. It troubled so much that he came up to this decision that God really does not play dice. Now the question that still remains with us is that in spite of that, he made the mention of the name of God. So did he believe really in God? What was Einstein's viewpoint on God? Let us see quickly and coincidentally in this part of our video. So you see that Einstein actually was averse to Abrahamic conception of heaven and hell, particularly as it pertained to a system of everlasting reward and punishment. So he said that I cannot conceive a God who rewards and punishes his creatures or has a will of the type of which we are conscious. An individual who should survive his physical death is also beyond my comprehension, nor do I wish it otherwise. Such notions are of the fierce or absurd egoism of feeble souls. Well, I would say this is one of his philosophical quotation. What is important is this: I am not an atheist. So we get something which has got respect for God. And don't think I can call myself a pantheist. I believe in Spinoza's God, who revealed himself in the orderly harmony of what exists. You see, I have made it yellow because this is what Einstein believed, an orderly harmony of what exists, not in a God who concerns himself with fates and actions of human beings. And this orderly and harmony of what exists actually shows his mind of classical determinism. He also said this, to be very honest, that my views are those of Spinoza, admiration for the beauty of and belief in the logical simplicity of the order. I would like to quickly tell you that this word, very important, logical simplicity of the order. So that means again it shows that Einstein believed in order, not in chaos. He believed in determinism, not in probability. He believed in classical determinism and certainty, but not in superposition and probabilities, what quantum mechanics says. And you will see that if you see my video on Tagore-Einstein conversation, I have exactly point on this. I believe that we have to content ourselves with our imperfect knowledge. And that is what he thinks to be God, somebody who has got the knowledge, but we are imperfect. But most important is logical simplicity of the order. Now, till his last days, Einstein struggled for a theory of everything. unifying all the four forces of nature and putting an end to all the questions of fundamental physics. Shall we ever achieve it? Will that put an end to our quest for the ultimate truth? Will mankind end his search when we have answered the final question? What are your views? Please let me know your views and comments in the comment section. I would immensely like to thank you for watching this video. I made it a little bit different and philosophical. Please subscribe and click on the bell icon to get all the notification from Physics for Students. You contact me at this email ID. You can further look into this channel which is dedicated to general relativity, and you can also follow me on my Instagram, Facebook and LinkedIn pages. Thank you for watching this video, and I will be back soon with more interesting video. Physics for Students will continue producing interesting videos, thereby making you physics and mathematics learn in a fun, loving manner. Thank you, and may the good Lord be with you. Goodbye.